Okay, so in 4.4, number 17 is a function, and the question is, find the points of inflection and discuss the concavity. So, you know, in order to do points of inflection, I need to get to the second derivative, which means I need the first derivative. And I think maybe I should say to myself, product rule. So if I'm going to do a derivative, I'll do a product rule, I think. The derivative of the first thing times the second thing plus write down the first thing and now take the derivative of this second thing, which is a 3x minus 4 squared. The chain rule says you do the derivative inside, but that's just a 1. So cool, we're finished. Well, we're finished with the first derivative. And then if I wanted to do a second derivative, I could sort of start here. I could start working on this second derivative. When I get over here, that's another product rule. You know, before I do the second derivative, I could clean this up a little bit. That's probably the smart thing to do. So let me just clean a little. If I'm going to clean a little, I would look at this and look at this and factor out what they have in common, which is x minus 4 squared.
Right.
So then what's left here?
X minus 4.
An x minus 4. And what's left over here? A 3x, actually. Combine like terms a little bit there, and that's a 4x minus 4. I'm happy with this. That's my first derivative cleaned up.
Right.
I could go look for critical numbers, and I could go look for maxes and mins and do a first derivative test. I mean, I could, maybe I should, but this question wasn't asking about that. This question wants me to move on to the second derivative and look for inflection points. You know, normally I kind of want you to do it all.
I know.
So, you know, a typical Scott Smith question would be, go ahead and do it all. Find the critical numbers, you know, so we could pause right now and do that.
Okay.
You want to do that?
Yeah.
Well, so when does this equal 0? I can see it real clear.
Yeah. X is
This
4.
equals 0 when
X is 4.
And
1.
And when x is 1. So those are critical numbers. Again, this is not part of the problem. X equals 4 and x equals 1. This is me adding a little to this. Those are critical numbers. If I put them on a number line, I can test and see what's going on. This is a 1. This is a 4. I'm going to try something over here to the left. I'm going to try a 0. I'm going to plug it in the derivative, and I'm going to very quickly get positive and negative, so that's negative. That's me talking quick and working quick. Plugging in a 2. That's positive, so it's positive. Plugging in a 5. That's positive, it's positive. So, cool. These were my critical numbers. I just tested around them. I just did a first derivative test as quick as I could. And I discovered that I have a min here. I think this is a min. Do you agree?
Yeah.
And this one, even though it's interesting, this is one of these places where the derivative was 0. This was a critical number. This x equals 4. It makes the derivative 0, but it turns out it's not a min or a max. It's a neither. By the way, I kind of know what that looks like. Something that's not a min or a max, but yet still a level place, you know? So that's kind of what's happening there. And by the way, after I draw that, then you might kind of realize that 4, this place here, it's not a min or a max, but it might show up in the second derivative as an inflection point. You can kind of see that, right? It looks like it changes concavity there. Right now, I officially don't know that. Yes?
Where'd you get the 4x minus 4 again?
I just, after I did a product rule, then I factored this out. And then I combined what was left.
Okay.
All right, anyway. So none of that was part of the question. This was though. But now I need a second derivative. If I'm going to do a second derivative, it's a product rule. You ready? Derivative of the first. 2. X minus 4 to the first. That's the derivative of the first. Okay, times the second. Plus, write down the first and take the derivative of the second. 4. To clean him up, I would factor out whatever they might have in common. Basically, it's that x minus 4. Maybe a 4 too, but I ain't worried about that. I'm going to factor out the x minus 4. If I factor out the x minus 4, I'm left with this 2 times this 4x minus 4. And then over here, I'm left with, I factored out an x minus 4. So I'm left with an x minus 4 times 4.
Right.
And then I would distribute and clean up. You know, after you factor that thing out, what's left can usually be cleaned up big time. That's how it always works. So this can be cleaned up very nicely here. What is it? It's an 8x minus 8 plus a 4x minus 16. Altogether, I think that's a 12x minus 24.
Right.
So I'm getting down to the bottom of the board here. I'm sorry. Sorry here, but there it is. That's a cleaned up second derivative there. Can you see it way down here?
Yeah.
Second derivative was a product rule. Factor out what they have in common, clean up what's left. And now, when does it equal 0? It equals 0 when x is 4 and when x is 2. Right, if I set these equal to 0 and solve, that's what that is, x equals 2, you're right. So those are my PIPs, my possible inflection points.
I was going to call them critical numbers for a second.
No.
Yeah, I know. Right.
Yeah.
They came from the second derivative. They're
Okay.
called PIPs. I put them on another number line and test the second derivative to see if they're positive or negative. I try to line up my number line so a 2 would go kind of here, a 4 would go here, and then I would test around here. I'm testing into the second derivative to see if it's positive or negative. And that tells me the concavity. These are probably good old inflection points. We'll see what happens. Pick any number you want out here.
0.
0. Plug it into that second derivative. That's a negative 4, but that's a negative 24. When you multiply those, that'll be a positive something. So it's positive over here. That means you're concave up. Let's pick 3 here. 3, 3, 3. That'll be a negative, but when I plug 3 in there, this quantity will be positive. So it's just a positive times a negative is negative. I mean, again, that's all I care about, you know, the positiveness or the negativeness. So we just decided that region is negative, which means the graph is concave down in that region. And then I could pick a 5. That's positive and positive, so it's positive. So that's concave up. So it really did switch concavity around these places. So these are legitimate, real inflection points here. So, cool. We found them. You know, again, one more thing, just what I would ask you to do probably is list this stuff. You know, what is the relative min? What is the relative max? And what are the inflection points? And if they're not too bad, then I kind of want the y values, the x's and y values. If it's a real pain in the butt, I don't like you to do that. In other words, if one of my critical numbers was 3 plus the square root of 17 divided by 7, do I want you to plug that in and find the y value? Probably not. If your critical number is x equals 1, can you plug it in and find the y value? Yeah, you can do that. But, so sometimes maybe my directions are clear, maybe my directions aren't that clear, but I think I'm reasonable. So here I go. Let me see. Did we find a min?
Yeah.
We did find a min. The min was at x equals 1. Can you tell me the y value? When x is 1, how do you find a y value?
Plug in the original, so it's
Go back to the original function and plug in a 1. I think you get 1 minus 4, which is negative 3 cubed. Everybody knows that's negative 27. So that's your y value. Hey, what about a relative max? What do we find?
None.
None. Thank you very much. What about inflection points? Oh, we got 2 of them. One of them was 2, comma something, and the other one was 4, comma something. Let's plot those and see where they live on the in the original graph. Okay, what did you say?
For the original, to find the minimum.
So I plugged in a 1, and I got, yeah, that's it.
Yeah, that's what it is.
All right. Right, I was plotting x equals 1 and plugged in a 1. Okay. Now I'm plotting x equals 2. When I plug in a 2, let's see, I get negative 2 cubed. That's negative 8 times 2. Negative 16. And when I plug in a 4, that's pretty sweet. I get a 0. So this is me just plotting points. I hope you remember this. I mean, I hope you know, there's a lot of plugging in, right? During one of these problems. Okay, we're finally finished, kind of. But there was a lot of plugging in. You know, what was I was plugging test numbers into the first derivative. Then I was plugging test numbers into the second derivative. Now I'm finally plotting points, so I'm plugging numbers into the function to plot points. Anyway, you can organize your brain and figure out where you're plugging stuff, I think. Right? Okay. Anyway, we're done. If I plot these points on a graph and then try to read this, I could sketch a graph. It'd be kind of cool here. Let's see what happens. Let's just see what happens. 1, negative 27. Okay, well, that's 1. I'm going to call that negative 27. 2, negative 16. 2, negative 16. 4, 0. That's interesting. 3, 4, 0. So those are my points. Let's see what happens. Look, watch. I like to read this number line and I'll end up sketching a graph when I read this number line. Left to right. You ready? Decreasing. Decreasing, concave up. Okay. I'm just going to start over here and I'm going to decrease concave up until it hits this min. After it hits this min, it's going to start increasing. By the way, it's still concave up for a little while until it hits that 2. See, when you hit the 1, you start increasing, but you're still concave up for a little while. So look, I'm still concave up. And then I hit that 2, and I continue to increase. In fact, I'm increasing the rest of the way. But I continue to increase, but now when I hit this 2, I switch concavity. I'm concave down for just a little bit until I get to the 4. So now watch, I'm concave down for just a little bit. When I get to the 4, I still increase, but now I switch concavity again, concave up.
Oh, wow. Okay.
So that's cool. I mean, that's an accurate picture of and that's accurate, increasing, decreasing, concave up, concave down. That's all very beautiful and accurate. I clearly see my inflection points and my min, and I don't have a max. And anyway, it all came out good, right? You know, again, one more time, I overdid this question. In 4.4, the actual question was find the inflection points. Yeah. So that was kind of just this part of the question, or this part of the question.
Okay, so when you find the first derivative, you could just go ahead and find the second derivative. You don't have to do all the extra.
Well, I did this extra, because, right, so it depends what you're doing, right? For their directions, all they wanted was inflection points. I overdid this problem, because on your quiz today, you might have to overdo this. I mean,
Yeah. I'm glad.
my typical questions are do it all. So I've turned it into one of my typical questions. But you're right, they weren't interested in the mins or maxes. They just wanted a first derivative. My advice, though, is if you still kind of got to do a first derivative and then still clean it up before you do a second derivative. But you're kind of right. You could have went all the way straight to here and then found your inflection points. to answer their question, right? Right.
And would you require the graph too?
Yeah, sometimes. I mean, a lot of times. Yeah. And the thing is, I'm doing this graph by reading these number lines and putting all this together. I mean, I worked hard, right? This is what this chapter is kind of about. I mean, if it all kind of summarizes into this. Take a derivative, set it equal to 0, look for critical numbers, put them on a number line, test them to see if they're mins and maxes. Take the second derivative, set it equal to 0, look for possible inflection points, put them on a number line to test whether they're really inflection points in concavity. But I mean, this whole process is kind of what this chapter is, except for some other little details. I mean, this is everything we learned, all in one cool problem. I like that. And then sketch a graph.
Yeah.
And so I'm doing all this very analytically. The calculus is proving all this to me. I'm testing this all. This is awesome. And I never did pick up my graphing calculator. You know, if you're supposed to sketch a graph, and I don't take away your graphing calculator, then this part of it should be pretty easy for you. But I am grading your work. So I'm grading you, I'm watching you do your derivative, I'm grading your derivative, I'm grading this work here, I'm grading this work here. You know, so I'm not just after, oh, cool, I got the graph with my graphing calculator. I mean, that counts for a couple points, but all this work kind of counts for most of the points.
So for the graph, it's just minor points.
Well, and I'm saying it's giveaway points because you have a graphing calculator, right? That's what I'm saying.
Right.
How would you put in a graphing calculator?
Right, maybe some of you don't know how to use your graphing. You type in the function, right, and you play with the window. I mean, right, there's a lot to using your graphing calculator, to tell you the truth. That's almost a whole nother lesson. You go to y equals and type this in and adjust your window. And after you plot all these damn points and you know what's going on, then you know you can adjust yourself a good window, actually. After you've done this complete analysis, I would know to, maybe go, I don't know, probably -5 to 5 on the x probably would be good. Maybe -30 to 30 on the y would be good. You follow me on that?
Yeah.
That's me using my common sense after I know everything to set a good window.
Yeah.
To get a good looking graph.
And then once you type that function there, you just click graph. And
Yeah.
That's it.
Yeah. Yeah. Right. You might need some graphing calculator help or lessons, but other people might too. I mean, I don't know. I don't know. I sort of feel like you know how to use your graphing calculator. There's been times this semester where we use it, but I've never really taught you much with it. Yes, sir.
Oh, can you do 53, please? And add the 4.4.
Yeah, let me see.
That's my sister's. I was like, hey, you already bought one.
All right. Hey, this is good, you guys. 53 and 4.4. The directions are a little funny, but anyway, the directions are to use the second derivative test. And I think I told you what that was one time, but I never really, I don't know if I did too many examples at all. Anyway, I haven't done any second derivative tests today. I call this a first derivative test. I call this process a concavity test. So that's kind of what we've done today. A second derivative test is a different way of testing for mins and maxes. And I'll tell you what it is again. You find your critical numbers, which are your candidates for mins and maxes, and you plug them into the second derivative. By the way, you haven't seen me do that today. But you take your critical numbers from your first derivative, you plug them into your second derivative, and that's called doing a second derivative test. The conclusion is, when you do that, if it comes out positive, that critical number was a min. If it comes out negative, that critical number was a max. So now I just described the second derivative test to you. Let's try to do it, I guess. So
If it's 0, it fails, right?
all right.
Which one is that?
You gotta go back to the first derivative.
Yeah, you're right. All right, anyway, I need a first derivative. It's a product rule.
2x.
2x times the other guy plus x squared times the derivative of the other guy.
Negative.
Good, which is himself, but the chain rule spits out a -1, right, you guys?
Right.
Good job. And I would clean this up by factoring out an e to the negative x. I wouldn't factor out an x, I wouldn't. I would just factor out an e to the negative x, and that leaves me with 2x minus x squared. Do you guys agree? All right, well, there's my derivative, pretty cleaned up. If I'm going to do a second derivative test, I will need a second derivative, but let me pause here and look for my critical numbers. How do you look for critical numbers? You
Equal to 0.
set this equal to 0. Right. So when does this equal 0? Well, you could set the e function equal to 0, but an e function never equals 0. So setting this equal to 0, the answer is never. Setting this equal to 0 requires just a little algebra. Now I'd factor out the x. I'd have 2 minus x equals 0. So this equals 0 when x is 0 or when x is 2. Cool.
Right.
So those are my critical numbers. I want to test to see if they're a min or a max. Usually I do a first derivative test, but this question wants me to do a second derivative test. So I'll do that.
You can do it all. Well,
Well, I don't want to. I'm going to do a second derivative test, like they asked. So here I go. How do I do a second derivative test? I plug those into my second derivative.
Get a second.
Well, that means I need a damn second derivative. All right. All right, another product rule. Derivative of the first. Negative e to the negative x.
Right.
That's his derivative.
Times 2.
And then I'm writing this down.
Plus.
Now I'm going to write him down. And then I'll do his derivative.
2x minus 2. I mean negative.
2
minus 2x.
minus 2x. All right.
Right?
All right, cool.
Okay.
Now I'll clean it up. Maybe. Well, I don't have to clean it up. I'll clean it up. I'll factor out an e to the negative x. What does that leave me with? It leaves me with a negative 2x minus x squared here. It also leaves me with this 2 minus 2x over here.
and then you combine like
I should distribute the negative, combine like terms. Right. That's a negative 2x plus x squared plus this 2 minus this. So that's an x squared minus 4x plus 2 when it's all cleaned up. Wow.
And then the negative x. And then I have to plug in.
All right, I'm pausing. I'm pausing. These pauses are well-planned pauses. Well, I mean, I did the second derivative and cleaned it all up. I'm pausing. Are you guys all right with this? Maybe I lost you somewhere, but maybe you're all right. And so a second derivative test says plug your critical numbers from your first derivative into your second derivative. If it's positive, it's a min. If it's negative, it's a max. That's what the second derivative test says. It's a little weird, but I explained it once. I explained the logic behind it once. All right, so that means I'm taking this second derivative and I'm plugging in a 0. That's my notation. I'm plugging a 0 into the second derivative. Well, that's e to the 0. And then it's a 0, and it's a 0, and it's a 2. I think e to the 0 is a 1. 1 times 2 is 2. The point kind of is that it's positive. And so since the second derivative is positive, at that critical number is a min. I'll tell you what the logic was. I'll remind you of the logic. The logic was this. If the second derivative is positive, that means it's concave up. If the graph is concave up and you're a critical number that lives in the middle of a concave up environment, you got to be
A min.
a min.
Yeah.
So it's logical why it works.
So this is just another way to test the first derivative number line, then, basically.
Okay, so this what I'm doing is called a second derivative test. And it is another way to test your critical numbers to see if they're mins and maxes. We already have a way to test our critical numbers for mins and maxes. It's called the first derivative test. And it uses a number line.
Right.
Right, you're right. Right. And I
That's
haven't.
where I was confused at, but now it's not. Now I understand it.
Well, it's a different test. It's called the second derivative test. We haven't gone over it much. So you might have been confused, right? We didn't go over it much, but here it is. It's not that useful because I already got a damn test to tell if what's a min and a max, right? This is a second way of telling whether I got a min or a max. You're right. If I already got one way, why do I need a second way? Well, you never know what kind of information you're given and what you know. Bless you. So maybe, I don't know. It's good to know. That's why I mentioned it. Let's try plugging a 2 into our second derivative. Let's just see what happens. Plugging a 2 into our second derivative means I get e to the negative 2. And then I plug a 2 in here. That's 4 minus 8 plus 2. I think that's a negative 2. You know, e to the negative 2 is just 1 over e squared. It's a little decimal is what it is, but it's positive. And it's positive. And then it's positive and it's multiplied by a negative, so this answer is negative. So if it's negative, you plug it. When you plug your critical number into this and it's negative, it's a max. Right. That's the conclusion of the second derivative test. That's good. These derivatives are good, right? These are good little product rules you got to do and clean them up. It's not. I mean, it's not the worst thing in the world. The one I did earlier. Well, whatever. You do a product rule, you factor it, and clean it up. Yeah, these are good. What else? Any other good questions? 4.259. Yeah, maybe. You know, so I did go into 4.2, and there was two ideas in there. There was Rolle's theorem and the mean value theorem. Listen, they didn't make today's quiz.
Yes.
Yes.
Well, they're not that bad. Since you're so happy, maybe I should adjust this quiz. I'll be right back. I don't know. Anyway, it'd be cool if you understood them. Let's try this one. 59 says, and it's thrown into the context of a word problem. We'll see how we can adapt it to the mean value theorem. It says, the height of an object, t seconds after it is dropped from a height of 300 meters is this. So they're giving me a height equation. Negative 4.9 t squared plus 300. Listen, you guys, this is just kind of a typical falling object problem. Somebody dropped this falling object from a height of 300 feet. They dropped it. As a function of time, it falls in the shape of a parabola and hits the ground at some point. Its height as a function of time is a parabola. This is in meters and seconds, so that number is, when we were in feet, that was always a 16. You guys remember that?
Yeah.
It was 16, it was half of gravity. Well, now it's in meters, it's 4.9, which is half of gravity.
Was the 16 positive?
No, it was negative because
Okay.
of gravity, kind of, yeah.
All right.
So anyway, this is just your classic falling object from 300 meters. So what's the question? Find the average velocity during the first 3 seconds. Well, see, I don't know if you get this. What if I asked, okay, let's say this. What if I asked for an instantaneous velocity? What would you do then? Take the derivative. Damn right. Thank you. You learned some calculus. Thank you. The instantaneous velocity is the slope at any particular instant, or the velocity at any particular instant, which is just like the slope at any particular instant, which is just like the slope of the tangent line, which is the damn derivative, right? So the instantaneous velocity is a derivative. But an average velocity is just sort of a good old average slope, which would be subtract your two y values, subtract your two x values. It would be distance over time. It would be find the position at 3 seconds minus the position at 0 seconds. That's my two distances being subtracted over my time being subtracted. Are you following me?
Yep.
Maybe? I mean, an average velocity is just an average slope, which is just the change in y over the change in x. Again, because it's velocity, it's change in distance over change in time. That's a velocity. That's what's going on here for the first 3 seconds. So let's calculate this. So this is an algebra problem. This is not calculus. An average velocity is just this slope. So let's calculate it. When you plug in a 3, I need to know that number, please. If you plug in a 3, 3 squared is 9. Multiply that. Can you tell me that number?
She said negative 44.1.
Plus the 300? 255.9. Thank you. Minus, plug in a 0, what do you get? 300. All over 3 minus 0. So those are my two y values. Let me just show you something. At 0, my y value is 300. That's a point on the graph. At 3, my y value was, what was my y value at 3? 255.9. So at 3, I was at this height. See, these were 2 points on the graph. And the average velocity was the slope connecting those 2 points. And that's what we're about to calculate here. What'd you say?
Negative 44.7.
All right, what?
Negative 14.7.
That's the final answer. Thank you. You did your numerator, you divided by 3, and this is your final answer. Feet per second, meters per second. It's a velocity. It's an average velocity. Cool.
Why do we divide by 3?
It's the slope between these 2 points. Subtract your y's, subtract your x's. When you subtract your x's, it's 3.
Okay.
It's a 3.
Okay.
Subtract your y's, divide by 3. All right, now, that's the average velocity. It's just a slope. I'm sorry it took me so long to explain it. Part B, use the mean value theorem to verify. I mean, this is what the mean value theorem says. Do you remember what it says? I mean, I remember. It says, I mean, I could read that, but it says that at some point between 0 and 3, there is a point where the instantaneous velocity will match this velocity. And you can kind of see that. I mean, there is a place where the slope of the tangent line will match this slope. You're guaranteed. The mean value theorem guarantees that there's a place in between there. Wait a minute. There was some, wait. For the mean value theorem to guarantee that, there was a couple of stipulations. This function has to be continuous from 0 to 3. Does it look like it's continuous?
Yes.
Yeah. It also has to be differentiable from 0 to 3, which kind of means no sharp points or bad places, and I think it's cool. It's differentiable. All right, anyway. And then what it says is the slope of the tangent line, which is the derivative, should equal this slope at some point. What is the derivative? It's the easiest derivative in the world, please. Negative 9.8t. So that's the derivative. And I'm saying at some point, negative 9.8t equals this negative 14.7. And let's find that place. find t. Divide by 9.8, divide by negative 9.8, and you get 1.5?
Yeah.
Exactly?
Right.
Okay, cool, thank you. Which actually happened right in the damn middle. Between 0 and 3 is 1.5. I'll be darned. I don't think it's always like that. Is it always like that? With an average velocity? I don't know. I'd have to explore some other problems and see.
So what does the 1.5 indicate?
All right, so let me read this problem. Use the mean value theorem to verify that at some time during the first 3 seconds, the instantaneous velocity equals this average velocity. Find that time. So the mean values theorem says that at some time between 0 and 3, there is a place where the instantaneous velocity equals this average velocity.
Okay.
And we found that time. There it is.
Is the average, that part, the second step there, isn't that the mean value theorem?
Well, it's in,
That's the mean value part.
right,
The
well,
theorem part.
sure, it's the average velocity. The word average does connect to the word mean.
Yeah,
The
because
mean
that's-
is an average, so you're, yes. And the mean,
And then when you do the instantaneous, that's when you do that one, so it. There's a
right.
value
I
there.
mean, the mean value theorem said that the function's derivative, the derivative at some place C will equal the slope between the two endpoints.
Yeah.
And then what we're doing is we're putting this idea from the mean value theorem sort of into a word problem where my slope between 2 points turns out to be an average velocity, and my derivative at a certain point is an instantaneous velocity. So this idea is just an abstract math idea for any old damn function, but put into this setting, it's an there is a place where the instantaneous velocity equals the average velocity. Right, right.
That's the mean theorem, or?
That's what it says, right.
Okay.
That's kind of the conclusion of it right there. What else? Yes.
On the infinity problems, 15 on 4.5.
Yeah, okay, let's check that out. And yeah, right. Right. So you guys, I went into 4.5 and I taught you, just barely kind of taught you a little bit about these limits that go to infinity. And if you remember though, maybe you remember, the connection I was trying to make was that these limits as x goes to infinity is really kind of a calculus way of asking you about horizontal asymptotes. And so then I didn't do too many of these problems because then I just decided, hey, you guys remember how to find horizontal asymptotes, and so I kind of just transitioned into that from good old pre-calculus.
Okay,
So-
if we do it the pre-cal way, that's okay.
Well, so you're right. So listen, on a test or a quiz, am I going to ask you some limit questions? I don't think so. But will horizontal asymptotes maybe show up on a graph or a function? And yes, that could happen. But we can still try to understand this. I am trying to. So in 15, there's these 3 questions. What was this one?
X equals minus 1.
Okay, thank you. And then there's this other one. Look at this one. As x goes to infinity. Then there's this one. X squared plus 2 over x squared minus 1. Then there's one more. And I like this because this is exactly what I wouldn't mind I mean, I know how to do these limits. So, I don't know. Listen, so there's two stories I can tell you here. Two stories, right? Ready? Let's do these damn limits. Ready? Forget horizontal asymptotes for a second. Please plug in infinity and tell me what you get. You kind of get infinity over infinity. Would you agree? Infinity squared plus 2 over infinity cubed minus 1. That's infinity over infinity. Okay, infinity over infinity is indeterminate. It's kind of like 0 over 0. You're not sure what it is until you think it through and work it out. But you can think that the damn 2 and the 1 are pretty damn insignificant when you're headed toward infinity. So you can sort of ignore those and focus on this and realize you sort of have infinity squared over infinity cubed. And if you sort of cancel the infinities, don't let anybody see this video, but if you sort of cancel those infinities, it's like you get 1 over infinity. Now, can you tell me what's happening now? Your numerator's a 1 and your denominator's blowing up. What does that do? It goes to 0.
Because if the numerator is less than the denominator is there.
I don't know. To me, it's just this denominator's. If this denominator's a 10, it's 1/10. Okay, let it get bigger. Let it be 100. Then it's 1/100th. Okay, let it be 1,000. Now it's 1/1000th. So as the denominator gets bigger, the fraction is going to 0. We should know that. That's very logical. That's all I really want you to know. And the truth is, canceling these infinities and looking at infinity squared, infinity cubed, that's really not good mathematics. But this is good mathematics. The denominator blows up quicker than the numerator. It heads to 0. The denominator goes to infinity quicker than the numerator. The fraction heads to 0. Okay, watch this one. Plug in infinity. Oh, you get infinity over infinity. But this time, because of the degree, I would call this the same damn size infinity. And if they're the same size infinity, then they sort of head to the ratio of leading coefficients, which is 1. So this time, the answer is 1. So up there, the answer was 0. Here, the answer is 1. And it's very logical. It's about the degree. These guys are going to infinity at the same rate. So it's the ratio of leading coefficients. What about this one? This is infinity over infinity, but the numerator is infinity squared. The numerator wins the race to infinity this time. And if the numerator goes to infinity quicker than the denominator, then it just goes to infinity. So it's about who wins. This one wins. What's this one? A tie? This is a tie. And this one, the denominator wins. This one wins. So it goes to 0 or it goes to...
So how do those two numbers apply to a horizontal asymptote?
Good. Right. Guess what? On this function, there's a horizontal asymptote at y equals 0. By the way, a horizontal asymptote is y equals whatever the hell it is. Y equals 100, y equals 50, y equals... So it's a horizontal line, is my point. So there's a horizontal asymptote, y equals 0. This one has a horizontal asymptote, y equals 1. This one ain't got a horizontal asymptote. It doesn't. When you go to infinity, do you approach some number? See, when you go to infinity, do you approach some number here? Yeah, you approach 0. That's your horizontal asymptote. When you go to infinity, do you approach a certain number? Yeah, you approach a 1. You guys following me? You approach 1. When you go to infinity, this approaches 1. When you go to infinity, does this approach a certain y value? No. When you go to infinity, this one approaches infinity. When x goes to infinity, the y approaches infinity, and there's no asymptote. There's no horizontal asymptote. All right, now forget calculus and forget limits. What were your rules of horizontal asymptotes? Your rules of horizontal asymptotes were when the denominator has a higher degree, it's going to be y equals 0. Do you remember that? I don't know. When they have the same degree, it's a ratio of leading coefficients. That was the rule of horizontal asymptotes. And when the numerator has a higher degree, there was no horizontal asymptote. It was actually a slanted asymptote. The point really being, I don't care about slant asymptotes, but the point is it ain't a horizontal asymptote. So I don't think I really want to do limits. We do them up in Cal 2. We do these limits again, and a little bit. I'm just kind of interested in tying this into the graph, which is tying the idea of limits to horizontal asymptotes. I'm really interested in horizontal asymptotes to a minor extent. You got to watch out. You know, those horizontal asymptotes come in this story, but they come in a different story. You know, an E function, you kind of got to watch those E functions. You know, just good old e to the x. I mean, it has a horizontal asymptote. You know, it looks like this. And anyway, over here, it has a horizontal asymptote. It approaches 0 here. It doesn't on the right, but on the left, it approaches 0, e to the x. What about e to the negative x? It goes this way. It has a, you know, earlier today, we graphed the hell out of, or no, what did we do? Anyway, we did one earlier today. We did that x squared e to the negative x. I never did graph it though, did I? What was I doing to that?
That was the second derivative test, wasn't it?
We were just, yeah, we just did a second derivative test. So we were finding mins and maxes. So I never did finish it and graph it. But guess what? He's got an asymptote. I'm not sure what he's doing. He's probably doing, but he's got an asymptote. That e to the negative x means he's got an asymptote. I mean, it has to do with, listen, so now I'm not doing my, right, see, in this discussion, I'm not doing my pre-calculus horizontal asymptote lecture, but I'm going to tell you something. If you take the limit as x goes to infinity, this thing goes to 0, and it wins, and it takes the whole graph to 0. As x goes to infinity, this approaches 0. So there is a horizontal asymptote at 0. But I'm not really using my degree rules. Now I really am using the limit as x goes to infinity idea. I'm sorry, you guys. It's this idea. If you drop him into the denominator, right, and take the limit as x goes to infinity, maybe you haven't thought about this too much, and I haven't taught you this too much, but the numerator goes to infinity, the denominator goes to infinity. But the nature of these functions, you know, x squared is pretty bad dude, man. He goes to infinity pretty quick. But you know who's a badder dude? E to the x. E to the x is a badder dude than x squared. Do you understand that language? It's kind of from the 70s, 80s. It might be a generational gap here. He's a bad dude. That's what we used to say. It's infinity over infinity. But I'm not comparing degrees here, but I'm saying this is a bigger, badder infinity. Do you understand that? Maybe you don't understand it. Maybe you need to, what do you do to convince yourself? How do you convince yourself that's a big, bad infinity? It wins. It beats the hell out of that other one. I mean, one way to, well, graph it, yeah. And then you'll see a horizontal asymptote at 0. You'll see what I had on the board. I don't know, what, like, plug in a 10 and see what happens. When you plug a 10 in your numerator, it's 100. When you plug a 10 in your denominator, it's e to the 10th. What is e to the 10th?
Very small number.
22,026.
A very huge number, 22,026. Right, so I'm trying to say these are both going to infinity, but an exponential infinity kicks squared infinity's butt.
Say it.
Yes.
It kills everything. How about that?
It does, kind of. You're right. An e to the x beats an x cubed. It beats an x to the 4th. It beats an x to the 9th. An x to the 9th ain't no competition for an e to the x.
Right.
In the race to infinity, e to the x wins. So the denominator wins. If the denominator wins, that the fraction approaches 0. That's the concept, right?
So in this case, with the x squared divided by e to the x is 0, right?
So the limit as x goes to infinity is 0, and that means there's a horizontal asymptote at 0, right? And I just, a few seconds ago, I speculated that this graph looked like this. But your graphic calculator would help you see that. I might have it upside down. Maybe. Sometimes they look like this. Sometimes they do something else, maybe. But when you head toward infinity, It's heading towards zero, I guarantee you that. Right. But anyway, what's the point? It's fun to discuss these limits. I like these limits. They're fun to discuss, but I'm not going to ask you about limits. I'm sorry. Too busy doing other things. I got to do first derivative tests. I got to do second derivative. I got to do concavity tests. I mean, I got too much other. I don't need to ask you about limits. Go into infinity.
Maybe one or two might be on the test.
I mean, there might be some easy question, but it won't be that. What else? Anything else you guys want to ask me about? Yes, sir.
Can you do like number 3 for 4.6?
4.6, number 3. Yeah, that's very relevant. Thank you. 4.6, number 3. Here's the function. It's x squared over x squared plus 3. Right, you guys? Is that what it is?
Yes.
All right, listen to this. I'm up in 4.6, and in 4.6, it's a summary of everything I've learned. So I think my directions say, this is a summary of everything you learned, do everything. That's what they say. So that's a hell of a job, right? I need a first derivative. And by the way, let's look up here. As soon as I look up here to do a first derivative, it's a goddamn quotient rule. That's going to be a struggle. When I finally get it nice and cleaned up, then I'm going to need to do a second derivative. See, this is a good example. I taught you this one day last week. This is a good example on a test where I might give you the first and second derivative already done and cleaned up for you. I showed you that one day. Rather than, because I'll make you do regular derivatives and I might make you do product rules. I mean, nothing, I can make you do anything I want, but to save time on a test, maybe I do these derivatives for you and give you these derivatives and you have to analyze the hell out of them, but at least they're done and cleaned up for you. You follow me? Yeah. So that's really what I would do on a question like this. But let's just pause here for a second and talk about asymptotes. Can you tell me about the asymptotes? Because this guy has asymptotes, I think. What is it? Do you know? What kind of vertical asymptotes does he have? Vertical asymptotes.
None.
When the denominator equals 0, we haven't discussed that a whole lot, but whenever the denominator equals 0 should probably be a vertical asymptote. When does that denominator equal 0?
Square root of 3.
No, she said never, and she's right. You could try it. When does x squared plus 3 equal 0? If you move the 3 over, you discover that it's imaginary. Yeah, it never equals 0. So, no vertical asymptotes. By the way, I might ask you, and you fill in none, I guess. But there is a good old horizontal asymptote. What is it? Good job, because the coefficient, because they're the same degree, they're both headed toward infinity at the same rate, and it's the ratio of leading coefficients. It's y equals 1. That's an old pre-calculus algebra idea, right? The horizontal asymptote is y equals 1. Cool. Now, if I want to find mins and maxes and inflection points, that's when I need my derivatives, right? Hey, let's say, and I really hate cheating, okay? So I don't want to use the word cheating. Let's say, anyway, this is not cheating. You have a graphing calculator. Can you type this in and check it out? This might be a good hint. But it's got a horizontal asymptote at y equals 1. See, one of the things, when you teach math for 20 years, and you know what all these things look like. I just know what all this stuff looks like. But you don't, so pick up your calculator and type it in.
Straight across, dips at 0, and then back up to the...
Yeah, I think it's this.
Yep.
I mean, this is beautiful. I love these graphs sometimes. I mean, look, can you imagine if you had a bowl of ice cream that was shaped like this? I think you could keep filling it up forever. I don't think it would ever spill. You see what I'm saying? Look, What if it was filled up right to here? Can you get a little more?
It
Yeah.
goes forever.
Can you get a little more? I mean, this never change. This never dives back down, so it's not going to spill out.
Yeah.
You could keep dumping ice cream in here, and it's always gonna. There's a concavity here that'll keep it in the bowl, dude. Or Cheerios, whatever. You can pick your food. I don't know. I just think it's a cool graph. This is. By the way, after you have the graph, and maybe this is again. I don't want to use the word cheating. Real cheating pisses me off. So I don't want to joke about cheating. So I'm trying to avoid a joke about cheating. But if you were shortcutting a little bit, here, you picked up your graph, you got this graph. Now, do you see a min or a max? Can you tell me about mins and maxes without doing any derivative work? Can you tell me about min? What do you see? You see a minimum at 0, 0. Okay. There's a minimum at 0, 0. Again, I'd like you to show me your work, but which involves a bunch of derivative work. But you're right. There's a minimum at 0, 0. What about a max?
No max.
I guess there probably isn't one. It's funny how this rises toward that asymptote. So it never really hits a max, I guess. And what about inflection points? Do you see any inflection points? You see 2 of them? Is that what you mean?
Yeah.
Yes.
Yeah.
You didn't mean it was at 2.
No.
Yeah, good. Okay, thank you.
2.
Right, because I don't know where they're at, but she sees them. She thinks she sees 2 inflection points. I think she's kind of right. I think it's concave up here. But somewhere, in order to turn and bend toward that asymptote, it had to switch to concave down in order to approach that asymptote and not cross it. You know, you can't approach an asymptote like this unless you're going to cross it.
Right.
So you got to approach that asymptote concave down. That's the only way you can do it. Cool. And then over here too. So you're right. You're right. I think there's 2 inflection points and there's a min. And that's the story of this function. Now he asked me to do this. I haven't done it, except that I've shortcutted it is what I've done. I didn't really want to do all this hard derivative work. Remember I said a few minutes ago, I'd rather just give you these derivatives. It's not that bad? All right, then let's go. I mean, I don't know. Here, a quick quotient rule ain't that bad. You're right. What? I bet you I can do it in 20 seconds. Ready? Derivative at the top, times the bottom. Minus, right down the top. Take the derivative at the bottom. All over the bottom square.
There you go. Now clean
That's
it up.
only been 10 seconds. Here, watch this. Now clean it up. That's a 6x over x squared plus 3 squared.
Right?
1 second to spare.
Right.
Wait, what? Wait, what?
So your critical number is x equals 0. Which
I actually already did
you
it.
I think I distributed this and collected a couple like terms. They canceled, and I think I did that right.
right. You did. You did.
Thank you. So this is my derivative. Hey, do you see any critical numbers? When does this equal 0?
0.
When the numerator equals 0, which is when x equals 0, that's a critical number.
Right.
Remember, we already predicted there was going to be a min at 0, but we got a critical number at x equals 0.
Mm-hmm.
Right, you guys?
Yeah.
When you set this equal to 0, the numerator equals 0
Right.
when x is 0. The denominator never equals 0. We already know that, so. So anyway, that's my critical number. I could go test it, but I already know it's a min. Right. Again, if you're showing your work and the directions say do a first derivative test, then you better do one. Even though you already know it's a min. But you could do one, because that's what you're asked to do. Pay attention to your directions. Do what's asked for full credit. Anyway, maybe I don't want to do a second derivative. Do I? Maybe I do. Derivative at the top.
Direction says.
Times the bottom.
Minus.
Minus. Right down the top. Take the derivative of the bottom. That's a 2 times the x squared plus 3 to the first times the derivative inside all over the bottom squared, which is to the fourth. You know what you do now?
Yeah, I know you
What do you do now?
You do it first.
You know what to do now?
Like term,
You can pull out the x squared plus 3 to the second on the top and on the bottom. You can pull out 2 and the other one.
cross out a bunch of stuff.
All right, hold on. You're onto it, but I don't quite like the way you're talking, but you're really onto it. Listen, she said let's factor out or pull out the x squared plus 3. So it's kind of here in the numerator, right? Again, this is your big minus sign. There's a term and there's a term, and they both have an x squared plus 3 in common. You should factor it out. When it's factored out, it'll cancel with one of those in the denominator.
Right.
Or you can sort of cancel it without factoring it out. If you cancel it here, and cancel one of them here. That works.
Oh, man.
I just factored it out and canceled it.
Yeah.
I factored it out and canceled it. That's what I did. So that helps a little, but we still got a mess here. I mean, what do we have? In our numerator, that's a 6x squared plus 18. I went ahead and distributed that 6. Over here, I got a 12x squared, a 24x squared over here. All over this x squared plus 3 cubed. You know, that's a negative 18x squared plus 18. If you set that equal to 0, when does this equal 0? This is fun. I think I got this cleaned up here. This is my second derivative. When does that numerator equal 0?
1 and negative 1.
When, at 1 and negative 1, right, you guys? If you set this equal to 0, I think.
Right. Should I be cube?
This is cube. Yeah. Thank you. Right? You move your 18 over. You divide by 18. X squared equals 1. X is plus or minus 1. Cool. Those are my possible inflection points. I should probably test them, but we kind of already know. Look, I think we found these inflection points is what we found.
That's right. Okay.
Anyway, we're running a little late here. Maybe we better quit.
Yeah.